This, as a summary, limits are used to measure what's happening around a value, not at a value itself. So when you measure f at a, that's f at a exactly as if you're looking only at the value a and you are looking at the image of a on the function. But limit as x approaches a of f of x does not, we do not look at f of a. Maybe f of a is defined, maybe it's not, maybe whatever. So you do not look at f at a at all. To the contrary, you look at left neighbors, which we call them a minus, and we study what is the pattern of the function values of those left neighbors as we come in closer and closer to a. And we look at the right neighbors, which is finding what is the pattern of the behavior of the function f of x as we approach a from the right, meaning with values bigger than a, closer and closer and closer to a. If those two values, the left and the right limit, are equal to each other, equal to L, then we say that the general limit around A without plus or minus, meaning from both sides, is also equal to L. It exists, in other words, and is equal to L, where L is a number, where L is a finite number. If limit as x approaches A minus of f of x, or limit as x approaches a plus of f of x is infinite, meaning the function is growing or decreasing without bound as we approach a from the left or the right, we say the limit does not exist. If the limit of f of x as x approaches a minus is finite, it's not infinite, but it's not equal to the limit as x approaches a plus, which is also a finite number, but both of them are finite, but they are not equal to each other, we say the limit as x approaches a in general, we say it does not exist, and it is written as DNE. Be very careful, please, between two different definitions. We say f of a is defined or undefined. Function values, we call them defined or undefined, because either f of a is a defined value or it's not. Whereas the limit as we approach a of f of x, we say it exists or does not exist. Don't mix up the defined with the exists and does not exist and so on and so like. All right, so let's look at graphs. Let's look at an example from the book where we have a graph, and let's read the limit of the function from the graph. See, let's look at this function over here. Let's read the questions and let's answer it. What is f at minus 2? See, when I say f at minus 2, this means that I need to find the function value. Where do I look? I look at minus 2 exactly. I don't look at neighbors left or right. I look at minus 2 and check where is the image of minus 2. And I notice the closed circle on top of minus 2. What value is that? 3. So I say f of minus 2 is equal to 3. So in part A, f of minus 2 is equal to, this is section 1.2 in the exercises section, f of minus 2 is equal to 3. Whereas in part B, they are asking what is the limit of f of x as we approach minus 2. What do? We have to split between the left neighbors and the right neighbors. We look at this. We draw an arrow in our mind, like a bracket here, in our minds. You do not really need to draw it. And you start choosing values, and those values become closer and closer to minus 2. Minus 2, you do not look at it. So as if there is a scratch line on minus 2 exactly. And you notice as the x values approach minus 2 from the left, what's happening to the function values? They are approaching 2. They are not approaching 3. So many students mistake that because f of minus 2 is equal to 3, then this is our limit. No. Limits do not... we do not look at minus 2 exactly. If we look at minus 2 exactly, that's f of minus 2. We just notice what the function values as we come closer to minus 2. What are the function values pattern? What are they coming close to? They are coming close to 2. And what are the neighbors from the right doing? So minus 2 plus on top of it from the right. As I approach minus 2 from the right and I look at the function values, what do I notice the function values are approaching? This line is approaching 2. This part of the function is approaching 2. So both the left and the right are approaching the same number. So we say that the limit at minus 2 in general exists and is equal to 2. What is f at minus 1? F at minus 1 is undefined, because if I look at minus 1 exactly, do I see any closed circle on top of minus 1? No. So f of minus 1, we don't say it does not exist. We say it is undefined. What is the limit as we approach 0 from the right, as x approaches 0 plus? So where do we look? We look at the right neighbors, which are from here. If you notice from here, if I choose here x values and look at their images, as I approach 0 plus, those images are approaching what number? 2. We say the limit as we approach 0 from the right is equal to 2. And this is how it looks like. If you want to see the full answer, this is how it looks like. So that's basically what we have to think of. This is how we manage it. So let's look at another example. Look at number 11. They are giving us what f of x is. This is the function f of x. It's equal to x if x is less than 1, 2 if x equals to 1. Between 1 and 2, it's 4 minus x squared, and x greater than 2, it's root x minus 2 plus 1. What we care about is the graph. This is the graph. What is f at 1, for example? F at 1 means that we have to look at 1 directly. We don't look left or right. We look at 1 exactly. And we search above 1 for the closed circle. We see this is the closed circle. So f of 1 we say is equal to 2. Whereas in part B, they want us to look at what is the limit from the left, meaning less than 1. So we choose values less than 1 and we start approaching 1, and then we study what the function behavior is. If you take this value of x here and you take the image on the graph, you will see it's here. And then come closer and closer to 1. What will the values be approaching? 1 as well. So the left limit we say is equal to 1. The right limit of f of x is equal to what? The right limit, you look to the right of 1 and you choose values on the x-axis, and then you take the images of those values. The images, as if you drew a vertical line and you see where it cuts the function. All of them in your mind, you can do it. You don't need to write it. As we approach 1, 1, 1, 1, 1 from the right, what is the function values? Those are the right images. This is 1. These are the left and this is the right. So as we approach 1 from the right, we notice that what are the function values approaching? They are approaching the number 3. Now looking at this, you will notice that f of 1 is equal to 2. Limit from the left is equal to 1. Limit from the right is equal to 3. This means that the limit in general at 1, since this limit is not equal to this limit, the left is not equal to the right, we say this limit does not exist. It does not exist. Another example. I wanted an example that has asymptotes, just to, alright, there isn't any in this section, but we'll manage later on in another section. Alright, before I move on, what do they also cover in section 1.2? In section 1.2, they also cover the fact that you can find limits from the graph, yes. So what we have already learned is that we can find limits and function values from the graph. What if we cannot graph it? So what do? Is there any other way? Primitively, and I want you to never use this method. It's a primitive method and we will never use it. I see people even in final exams using this method This is called a numerical method. We never use numerical methods to find limits. What we use is we use graphs, or we use algebraic methods, or we later on learn calculus derivative method called L'Hopital's rule. But we never use this primitive numerical method. But I like this method, and I like to show it to you. Because, to be honest, it kind of illustrates for you the meaning of a limit. See, many students understand the meaning of a limit, but they don't really focus on it, and they don't really know what it means exactly. For that reason, I will show you what numerical method is. See, f of x is equal to x squared minus 4 over x minus 2. Or another g of x is equal to x squared minus 5 over x minus 2. See, those two functions look the same thing, and I want to do the same explanation that I did in the first video, but now without having graphs. I'll show you the graphs in the end, but I want you to not focus on the graph, to see how you can, using calculus methods and limits, understand that those two functions behave differently and their graphs are different. Although the first moment I look at them both and I ask, what is the domain? What to do when we have domains? Of course, domains are the values of x where the function is defined, is the largest interval of real numbers where the function is defined. If you notice here, this is a polynomial, it's defined everywhere. This is a polynomial, it's defined everywhere, but because it's in the denominator, it cannot be equal to 0. So x cannot be equal to 2. This means that the domain of these functions is all real numbers except 2. This here has the same problem. If you notice, x squared minus 5 is a polynomial, it's defined everywhere. X minus 2 is a polynomial, they are defined everywhere over all real numbers. But my problem is that I have division. When I have division, the denominator cannot be 0, which means x is not accepted to be 2, which means again that the domain will be all real numbers except 2. If I look at those two over here, I will notice that they are behaving the same way at 2. So students or people in general, if they see this scenario, what do they think? They think that those two functions behave the same way. To be honest, they don't behave the same way. Let me show you even a simple graph of x squared minus 4 over x minus 2. It's a straight line with just a hole at 2. Whereas x squared minus 5 over x minus 2 is kind of a hyperbola, and it has an asymptote at x equals 2. So do you see the different scenarios? Let me show you one more time. Do you see the difference between the two? So obviously they aren't the same. So imagining from this single piece of information that we wrote over here that they are the same is not fair. So how will we know that they are really behaving differently? See, if I look here at how in both of these, f of 2 is undefined. And here f of 2 is undefined. Here, the limit as we approach 2, this is what we're going to study. The limit as we approach 2 from the left, because we can never study a limit in general now, so far. So we will study the limit from the left and the limit from the right. But what I'm going to use now is I'm not going to use the graphs. I'm going to use the pure original concept of limits. What I'm going to do is I'm going to take x values that are close to 2 from the left. What does it mean close to 2 from the left? It means they are less than 2. And what will I do to those values? I will make them closer and closer to 2. So I will choose values less than 2, and I will make those values closer to 2. Like 1 is less than 2, but 1.5 is less than 2 but closer to 2. Then 1.9 is less than 2, closer to 2. See, I'm choosing values with a pattern. I don't randomly choose values, because then it will take me a long time to sort it out. So 1.99 is closer to 2. smaller than 2. 1.999, 1.9999. Those are all smaller than 2. But notice the order, the pattern I took. They are smaller than 2, but as I go down the table, the values become closer and closer and closer to 2. Now what do I do? What are limits about? Limits are studying the pattern of how the function is behaving at those numbers. At 1, you take the calculator. What is f? It's x squared minus 4 over x minus 2. If you plug it at 1, you'll get 1 minus 4 على 1 minus 2 is minus 3 over minus 1. The answer is 3. 1.5 squared minus 4 over 1.5 minus 2. The answer will be 2.5. 1.9 squared minus 4 over 1.9 minus 2. The answer, if you try it out, you will notice it is, this is 3.5. This is 3.9. This 1.99, also check it out on a calculator. You put it here, 1.99 squared minus 4, 1.99 minus 2. You'll notice the answer is 3.99. Here you will notice the answer is 3.999. And here the answer is 3.9999. Let me show you. I didn't really generate those numbers from on my own. I just used the calculator to show, to find an answer. So you just take the value that you have, like 1 squared minus 4 over 1 minus 2. You get 3 for the first one. Then you change from 1 to 1.5 up and down, and you get the answer, which is 7 over 2, 3.5. Then you move from 1.5 to 1.9, and you sort it out. Do you see what I mean? You get 3.9, and so on. So like, you try them out all. This gives you a table. This table, we call it table of values. From those table of values, because we have set up a pattern in the x values that we have chosen, what are x approaching? X approaching 2 from the left, because it's approaching 2, but it's smaller than 2. We say x is approaching 2 from the left. And then we study what the function values are approaching. What do you notice? The more we come closer to 2 from the left, what are the function values coming closer and closer to? They are coming closer and closer to 4. So we say that this limit from the table can be deduced to be equal to 4. What do we do in order to find the limit at 2 plus of the function? We do exactly the same idea, which is a table, but now how do I choose the x values? I choose the x values to be greater than 2, but they are approaching 2. We always have to approach 2. We have to come closer to 2. So for example, we choose 2.1 is above 2, close to 2. Then 2.01 is closer. 2.001 is even closer. 2.0001 is even closer, and so on. You can choose as many values as your time allows. When you substitute this in the function, again, what do you notice? 2.1, when I substitute it, I come here, I change it to 2.1, and so on. I will figure out it's 4.1. This will give me 4.01, 4.001, and 4.001. We notice that as we approach 2 from the right, what are the function values approaching as well? They are approaching 4. Is the limit from the left equal to the limit from the right? Yes. So we say the limit as x approaches 2 in general is equal to 4. Nice. So the limit exists. So although f of 2 is undefined, the limit exists and is equal to 4. Whereas for the second function, this, if I do exactly the same thing, x and f of x, and I set up those table of values, what do I notice? If I choose, again, here I will work with the left, so x will be approaching 2 but less than 2. Here I will work with the right, x approaching 2 but greater than 2. And I start choosing values. Again, I need to choose them less than 2, and the pattern should be the next term is always closer to 2. Closer. Can I choose any other values? Yes, you can choose whatever values. But then I thought instead of thinking of random, choose 1.8, then 1.88, then 1.97. This is randomness. I tend to choose those. They look more of a pattern. But of course, you can choose whatever numbers you want, as long as those numbers in the end are coming closer to 2 and smaller than 2. Over here, when you choose it, you go to this. See, instead of -4, this has to become -5. And the answer is 13.9. We do exactly the same thing. Here we will get 103.99. Here 1003.999. Here 10,003.999. What do you notice? As we come closer to 2 from the left, what are the function values? What's happening to them? They're growing very fast. They're growing without bound. Look at how the value here became. It was 13.9, then 103, then 1003, then 10,003, and so on. So what do we say the limit from the left is equal to? As we approach 2 from the left, since the values are growing without bound, this is exactly typically what we say the limit is plus infinity. Here we want to choose values that are close to 2 but bigger than 2, and they become closer and closer and closer, so that we can generate a pattern. What we notice is we take here 2.1 squared, or 2.1 squared minus 5, so that, what do we find? Minus 5.9. We do exactly the same thing here. We get minus 95.99, minus 995.999, minus 9,995.9999. What do you notice? As x approaches 2 but from the right, what's happening to those function values? They are becoming smaller. They are decreasing without bound. They will keep on decreasing without bound. What is typically that limit? We have talked about it before. It is minus infinity. Do you see this? This is exactly the idea of having a vertical asymptote. So if you notice here, it's unlike, although only one number differed, it was x squared minus 4, it became x squared minus 5. Although it's only a number of difference, we notice that the scenario is different. Here the limit does not exist. We say it does not exist because they are infinities. And on top, we can directly realize that x equals 2 is a vertical asymptote, just as the graph indicated when we were talking. If we go back to this function that we have over here, what do we notice? This original function that we started with, x squared minus 4 over x minus 2, can be written as x minus 2 into x plus 2 over x minus 2. Which means that x minus 2 and x minus 2 can be cancelled, but which gives me x plus 2 as a final answer, which is the straight line that we saw in the graph. But we can only cancel a factor in math if we guarantee that factor is not 0. So to guarantee that factor is not 0, so we can cancel that for all values of x except x equals to 2, because if it's equal to 2, 0 and 0 cannot be cancelled. So that's why this function is typically exactly the same as this straight line for all values of x that are not equal to 2. So that's why if you look at the graph, this function had this graph of a straight line. You see the straight line, x plus 2. The straight line with only one hole. Where is the hole? The hole is at 2, because at 2 that function is not defined. Whereas x squared minus 5 over x minus 2 cannot be sorted out the same way. I cannot factor and cancel things out, so it has to stay exactly as such. And its graph is what? It has a vertical asymptote at x equals to 2, and the function is more complicated than the function that is x squared minus 4 over x minus